No, not this Friday, but next Friday, right? That exam is going to be chapters 5 and 6. Chapter 6 is really short, but
we can tell.
but I want to. But I just want to show you what we're going to do. I'm pretty sure that we'll have plenty of time to cover the material in class, but what I want you to do, and I'll send these links out to you, is I have some screencasts for the online course, and I want you to pick up a couple of those screencasts before next week. I'll send you a link out, and it's like 10 or 15 minutes worth. Where are they? It's mostly probably stuff that you've seen before. Reflection and refraction, pretty simple stuff, sort of the nature of light kind of thing, which you might have seen in high school. That is light a particle or is it a wave? I'll send you the links for this, but we're going to be doing, I want you to pick up screencast 55, 56, and 57. And again, it's about 20 minutes worth of stuff. But we'll practice some of those things in class and we'll review some of the questions, but I won't go through the notes and watch all the clips and stuff. All right? Is that clear what I mean?
You're going to send us those?
I'll send them to you over email today or tomorrow. But if you could just do that by next Monday, we'll probably be in chapter 5 for the rest of this week. But then on Monday and Wednesday, we'll go through chapter 6. Maybe on Friday. Okay? Don't be afraid, though, because chapter 6 is really just the law of reflection. But you might know, do you know the law of reflection? It says that if you have a reflected ray, the two angles are equal. And then the law of refraction, which is also Snell's law, which you might have seen. The law of refraction.
Yeah.
You did in lab? Good. Okay. Nothing terribly complicated. It's really just a prelude to the next chapter when we get into optics, geometrical optics. But I want to get it on that next exam. Otherwise, the last exam is going to be really long. Too big, yeah. All right. Exams for this past test, let's see, were they good or bad? I forget. Have I seen y'all since the last test? I have not, have I? We had one class on Wednesday? Okay, yeah, the exam was really good too. But I'll hand it back to you today, if I remember. I'll remember. Y'all remind me, please. Was there any news from the weekend? Anybody married? Have a baby? No?
That's kind of extreme.
I think it wouldn't
look like
That would be news, but I always ask my other class that, and then I learned recently that one of the students got married, like this semester. And I asked that question on occasion. She didn't tell me. It was a lady actually. I just found out because she put she like hyphenated her last name now, so she did that on the assignment. She didn't think of the report it. Tell me. All right, we've seen the cross product before. Y'all probably haven't seen it in calculus, have you? Seen it in calculus? It usually doesn't come till calculus 3 in vector calculus. But we did do the cross product last semester, I believe, right, with the torques. We're going to see it again in this chapter because it gives the force that a particle feels in a magnetic field. Well, let's just sort of a little bit of review because some of you might not have seen the cross product if you didn't have me last semester. But the cross product, it's also called the vector product, is the product of two vectors. This is in contrast to the dot product, which we also did last semester. Remember, the work was the dot product of force and displacement. The dot product is the product of the scalar components of two vectors, so it's the scalar product, we call it. The result of the cross product is orthogonal to both of the two vectors. So if I have a vector that is in this direction and a vector that's in this direction, a vector that would be orthogonal to those vectors would be along which axis? I have one on the x and one on the y, along the z-axis, either the plus or minus z-axis. And so orthogonal just means perpendicular. It's a fancy way of saying perpendicular. It might have some fancier meaning than perpendicular, but I don't think so. You'd have to ask the mathematician. I think it just means perpendicular for all we're concerned about. The magnitude of the cross product is equal to the area of the parallelogram that's bordered by the two vectors. So if these are my two vectors, A and B, this is B, this is A, whatever this parallelogram is going to be the magnitude of my cross product. And the area, you don't really need to know about the parallelogram, but you do need to know that the area of the parallelogram is given by this. Can I go down to the next page? I'll give you a second. But mathematically, the product of the vector product or the cross product is the area of this parallelogram. And then we can find the area of that parallelogram looks like this. It's just the base times the height, but the base times the height is going to be dA sine theta. All right, so then our definition of the cross product, or the magnitude of the cross product, is going to be the magnitude of the vector A times the magnitude of the vector B times the sine of the angle between them. You can also think about it in terms of that you're taking the product of one vector times the component of the other vector that's perpendicular to the first vector. And so if I was doing AB sine theta, let's say that my vectors look like this, kind of like what I had here. I have the vector A here, this is the vector B, and this is the angle theta between them. Then it would, let's say I wanted to take the component, the y component of vector A, it would look like this. So that would be equal to A sine theta. And so I'm multiplying the magnitude of this vector times the magnitude of the A vector that's perpendicular to the first vector, taking two components of the vectors that are perpendicular to one another. Okay. It has lots of applications in physics. We saw it last semester with torque. Remember, torque was R cross F, because we wanted to know the force that is perpendicular to the moment arm, because that's the force, the part of the force that causes a torque. And we're going to see it also here with the force on a particle traveling through a magnetic field. And then that'll have a lot of applications for, like, for example, electric motors, mass spectrometers, electric generators, what have you. But this is how we determine it. Let's do an example. If I have two vectors, A and B, let's say that the vector A is AXI plus AYJ, and the vector B is BXI plus BYJ. You could have a third component to this too, a Z component, but we'll just take it like that. The cross product will look like this. I can just write it out longhand. It'll be AXI plus AYJ crossed with BXI, BYJ. And then you can just use FOIL. You remember FOIL? First, outer, inner, and last. Right, good. 8th grade math. So we use FOIL to expand the product. And so I can say AX, BX, I cross I, plus outer, which is AX, BY, I cross J, plus inner, AY, BX, I cross I, plus last, AY, BY. Did I mess up something?
Yeah, it's IJ or JI.
This, okay, JI. Right, J cross J. Alright, please note the change that I made right here. It should be J cross I. Alright. Now some of these terms fall out based on our definition of the cross product. A cross B, AB sine theta. The magnitude of A cross B the magnitude because the result of a cross product, unlike a scalar product, is a what type of quantity? It's a vector quantity. That's why they call it a vector product. All right. Which of these go away? Right, because for I cross I, this angle theta is 0, and the sine of theta is 0. Right. And we're taking the product of two perpendicular vectors, and I cross I are two parallel vectors, and so their cross product is 0. So I can get rid of two terms here. I cross I equals 0, and j cross j also equals 0. So I'm just left with ax by I cross j. And AYBX j cross I. Now we're going to use the right-hand rule. Have we done the right-hand rule in this semester yet? We did it last semester. No. Okay, we're going to use the right-hand rule. There's a picture in your book of a hand. You're going to use your right hand because we're using a right-handed coordinate system as opposed to a left-handed coordinate system. So we're going to use our right hand like this. And our index finger is going to give the first vector, A. The middle finger is B, the vector B.
The ball does not enjoy being flipped off.
Right, and then the thumb is the product of those two. I have a buddy, by the way, who he's in the psychology department, and he has like a thing that he always does. Like whenever he sees you, he does this, like peace, right? And it makes him look really cool, I think. Like it's cool. It's like, oh, it's Dennis. He does the peace sign, and I was like, well, I told my wife, I was like, well, I need something like that, something, that would make me look cool like that. And I said, well, maybe I could just flip the bird to everybody, but not like in a mean way, but just, like that's my thing, right? Like he does the peace sign, and I do the middle finger.
Why don't you just do the right hand rule?
I could do the right hand rule. Yeah.
Except instead of using one finger, you can use the rest of your hand.
Yeah. That's kind of cool, actually.
Ways.
Does he do this? He does this to people? Yeah. I need a thing, y'all. I need a thing. Anyway, so we're going to use the right hand rule.
Why don't you just go to the file and say, hey.
Yeah. So there are lots of different ways to do this, and we're going to see the right hand rule a number of different times in this chapter, but another way is you can let your fingers go in the direction of the first vector, and then they fold towards the second vector. That's the same thing, right, as this. My fingers go in the direction of the first vector, and then they fold in this direction of your middle finger. And then your thumb of the right hand gives the direction for the resultant vector. So if I'm taking I cross j, I is in this direction, j is in this direction, then what is the direction of that resultant vector? We would let our index finger go in this direction, and then our middle finger point in the direction of j, and then our thumb comes out of the page. Right? So the result of I cross j is k. And then, as you can imagine, the result of j cross I, well, what is the result of j cross I? Is negative k. In fact, anytime you have a cross product, it's going to be orthogonal to both of the two vectors. And so if I have a vector in the x direction and a vector in the y direction, then I know that the cross product has to be in either the plus or minus k direction. It has to be orthogonal to both of those. All right, so let's see here. So let your finger of your right hand, the index finger or the pointer finger, your right hand, because we use a right-handed coordinate system. Now, if you go online, you'll find some left-handed rules as well, but I don't know where those come from, but we're not using those. All right, we use the right-handed coordinate system.
They come from sketchy people.
They come from YouTube, and there's all sorts of crap on YouTube. All right, so let your index finger of your right, huh?
I said you use YouTube.
There's a lot of good stuff on YouTube too, but and then your middle go in the direction of the first vector, and the middle finger go in the direction of the second vector, and and then the thumb of your right hand gives the direction of the cross product. All right. So if we were doing these I cross J, J cross I can go in a second. And go on down now. All right. So as we've already said, I cross I is 0, J cross J is 0, I cross J is K, and J cross I is negative K. So as one quality of cross products is that A cross B is equal to the negative of B cross A. That's an attribute of cross products. And we saw that here. And if I switch the two terms, it negates the result. And then, so if I wanted the result of my original cross product, it's going to be AX BY in the minus AY BX in the K direction. This negative coming from the fact that J cross I is negative K. And then you would just put in whatever your numbers are, and then that would be the result. We'll do an example later. All right. There is a way, and if you've had Calc 3, you might have seen this, how to do cross products using like a matrix type form. And y'all are welcome to do that if you like on the test. But we use the right-hand rule a lot in some of the other applications in this chapter, so we're just going to do it this way. But if y'all know what I'm talking about, you're welcome to do that. Or if you want to look online, you can find it. I don't know that it's any easier, but if you're used to doing it that way, it might be. All right. Have any questions about cross products? Y'all remember this from last semester, sort of, maybe, kind of? Yeah. All right. We've seen these signs before, but I just want to remind you of them when we're drawing things in 3 dimensions. And by the way, I think that that's probably one of the more useful parts of this chapter. Vector calculus has all sorts of useful applications, and obviously electricity and magnetism is very important. But just thinking in 3 dimensions is also very important for you. It's a different way of thinking about things. And so when you're dealing with vectors in 3D, it sort of makes your mind think about different things in a different way. But anyway, so the way we denote the negative z direction or the minus k direction looks like this. I'll either draw just an x or an x with a circle around it, or sometimes I'll draw a whole field of x's. And we'll see that in all 3 situations. To have the z direction is a dot. Also, the x is like an arrow going away from you, because an arrow has a feather on the back, a fletching, and it's like it's going away from you. But if you have an arrow coming towards you, you don't see the fletching, right? Have you ever had an arrow come towards you?
No.
Have you really? Yeah. It just looks like a little point that's coming right at you from the...
I've had a dart thrown at me.
Okay. So sometimes we'll draw it like that, sometimes as a circle around a dot, and then sometimes just with a whole field of dots. Like if we're drawing a magnetic field, a region of a magnetic field that's coming out of the page. All right. So those are cross products, and we're going to use them with magnetic forces, and we'll work through some problems soon, just to remind you how to do cross products. But very likely to see this on the exam in a variety of different ways. And if you look back at old exams, they're always on there, calculating a cross product, given a force, or a velocity, or a magnetic field. Any questions so far? Remember the right-hand rule? I think that's my thing now.
Maybe you can do something like 5.
Oh yeah, that would be cool.
Yeah.
Uh-huh.
Something like that.
Right. Do y'all have things that you do? No?
I play the guitar.
I think it's just I'm pushing 40, right? And so now I need a thing to make me look.
Kids think you're cool.
No, to just make me look hip. I think, right? I get a
I'm
motorcycle.
not saying you're hip, but you are not hip.
All right. So magnetic forces. If I have a charge that's moving through a magnetic field, it experiences a force, and we'll deal with this quite a bit. That force is given by the magnitude of the charge times the velocity vector crossed with the magnetic field vector. So QV cross V. By the way, whenever I have a constant, so if I have, say, a constant, I don't know, let's call it 2, A cross B, then that is going, the magnitude of this, we'll just multiply that as a scalar quantity. So it's just going to be 2AB sine theta. All right, so if I have a constant, I just multiply it through. The magnitude of this force is given by QVB sine theta, where I take the magnitude of the velocity, the magnitude of the magnetic field, and the angle between them, where the velocity vector is here, magnetic field vector here, for example, and this angle theta is just the angle that's measured between those two. SI unit for the magnetic field is Tesla, like Nikolai Tesla, and it is named after him, Nikolai. I think there was a movie about him, right? The Prestige, right? That was all about him. He's kind of a quirky guy. The abbreviation for this is the capital T, because it's a person's name. And then sometimes you'll see this expressed in Gauss. We won't use this unit, but I think that y'all might have used Gauss in the lab when you measure the magnetic field of the Earth. Is that right?
I think so.
Yeah, well, 1 Tesla is equal to 10 to the 4th Gauss. So it's just another unit for magnetic field. Let's do a few problems just where we're finding the direction. All right, we'll use the right-hand rule to find the direction of the force that's acting on these particles. Right. And as we said, the force is always going to be perpendicular or orthogonal to all the others. So what is the direction of the force on this first particle? You'll see a variety of multiple choice problems where there's stuff like this. Take my right hand, my finger go in the direction of V. My magnetic field. Yeah, it's like that. And so what is the direction of my force? It's out of the page, right? Or we'll do a bunch of these, so if you're not getting it right away, that's not a big deal. So the force here is out of the page. How about this next one? Let's see, so V is in that direction. V is into the page. So what's the direction of the force? It's to the right. So the direction of the force, looks like that. All right, yeah, V is out of the page, or no, excuse me, V is into the page, and so it looks like this. Now on this next one, V is in that direction, V is down, and so what's the direction of the magnetic field? Or the, excuse me, the force? Right. What do y'all think? You'll try it on your own. Are y'all guessing? Is that a guess? No. Let's see. So V is in that direction. V is down. That's to the right, isn't it?
Towards you. You're going to spin your finger around.
What's that?
What is the index finger's pointing?
Yeah, the V is coming out of the page on the paper.
And then the other one's going in with the same direction. Would that be left on the other one?
Did I do this wrong?
Yeah, that's another one.
Oh, that's right.
Yeah, that's
This one I like.
switch your name.
All right. So what do we say on this one? What is it?
Right.
Right? That's right. All right. Sometimes you're given the force or the velocity and asked to find one of the other two vectors. So here you sort of have to work backwards. And so, for example, on this first one, you have the force in this direction. Which one's the velocity? Index or middle finger? It's your index finger, so it'll look like that. And so what's going to be the direction of the magnetic field that causes this force? Right. So this is our magnetic field here, not our force. Try this next one on your own. So where your thumb is the force, V is your index finger, and then your magnetic field is your middle finger. Look at that. You know it has to be either down or up, right? Because that's the only direction it's orthogonal. So F is in that direction. V is into the page. That's right, actually, so it's down. We'll try the next one.
You know, I gotta twist my hand.
Yeah. I understand that like draftsmen use this trick a lot. Is that true? Are you a draftsman?
We use the engineering,
Engineering.
yeah, the statics when we're doing producing three-dimensional.
Uh-huh.
We use it different ways, but it's usually just the circle, the I, the J, the K. You go one way, so it's easier.
Yeah, I tried looking in that book. I couldn't find it on the
Couldn't
page.
find it?
Yeah, it says
Yeah,
chapter
it's
2.
just it's basically a circle. You got I, J, K.
Uh-huh.
It shows the arrow going this way positive, and then the other way is going negative. So if you go A to the J, it's K, it's positive. If you go K to the J, it's I, it's negative.
Oh, okay.
It's just a little, it's a little graph, and that's basically.
I'll look again and see if I can find it.
It's like chapter 2.
Right. All right, what was this one here? Right. F is down, V is out of the page. Yeah, so it's to the right. All right, let's try this quick test.
Can we get excuse for the test if we twist our hand?
Maybe I could bring in like a model of a human hand, like a big foam hand for you to use or something. All right, let's try this one. Oh, so by the way, if you have a negative charge, you just use the right-hand rule, but then you take the opposite of the answer that you get from the right-hand rule. So if your charge is negative, you just take the opposite answer. Try this one. Yeah, if you get it wrong, I'll break your finger.
Oh, man. Is that a Colombian drug cartel?
Right, yeah, uh-huh.
We didn't steal from you.
Don't tell anybody I said that. Looking good.
So are you saying that whatever we get from our hand is the complete opposite of it?
Right, it's just you take the opposite. If you have a negative charge. What's the problem with anything?
Every time you press something, it says
I'm not sure. We'll look at it. Alright, just a few more seconds. We're still missing at least one other person. Okay, there we go. Anything, try it again? Try it again. Okay, alright. Okay, B is right. So, let your fingers go into your index finger go in the direction of B. Your magnetic field is out of the page, so it's like this. And so your thumb's to the right, but it's a negative particle, so it's to the left. Another way you might see this, like I said, if you look on YouTube or whatever, is this way I've always taught it. Is if you let your fingers go in the direction of B, and then they fold towards B, Now V is out of the page, so it'd be like this. And then your thumb goes to the right. Or even another way that people show this is that they talk about the magnetic field coming out of your palm. So then you don't have to do all this business. You can just have your palm and imagine the magnetic field coming out of your palm. Don't do this for the test, but you can do it between now and the test, and you can go along and you can put a big V on your palm, and then a big F on your thumb, and a big V on your index on your fingers. And that way you'll remember that, oh, well, if I have my
Everyone's
force
gonna think
here,
you're
my
crazy.
magnetic field, my velocity.
But everyone already thinks I'm crazy. Everyone already thinks I'm crazy.
Yeah, so it doesn't really matter, right?
For me, everyone else here is considered sane, but I stay using it.
All right. We'll see that again in the concept test. What, Catherine? Yeah, I was just thinking about that. Like, what if you got a tattoo? Like a real tattoo.
You should do that.
Permanent markings can do the trick.
If you got a tattoo, then that might get some extra credit. If you got F, B, and D on your right hand.
What kind of encouragement is that?
Huh?
You should do that to be hip.
Yeah, don't get a tattoo.
Yeah.
What kind of gang signs is that?
Okay, let's just do this quick example. You could have something approaching this. I mean, probably on your exam it'd be a little more complicated. But first, this is I give you the velocity and magnetic field vectors, and then I want to know the force and vector notation, and then also what is the magnitude of the force. Right. So F is equal to QV. Cross B. What was that? An iPod?
Siri.
Oh, it's Siri. My kids, sometimes I have my iPod in my pocket. My kids will give me a hug, and then it makes that sound because it pushes the wrong button or whatever. And so now my little boy, it's like every time he gives me a hug, he's trying to push on or trying to find my iPod. All right, so I'm just going to leave Q here for now. We'll multiply it out later because it adds a lot of numbers. V is going to be 2I plus 1J crossed with 1I minus 3J. I'll leave you there for just a minute, so go ahead and do that cross product. Just leaving out Q for now, and just do the cross product. I'll give you a bit of a head start. Remember your I cross I and J cross J terms go away. That's our F and L. So really all you're doing, instead of FOIL, you're just doing OI. Just the outer and inner. So I got the outer is minus 6 I cross J, and the inner is plus 1 J cross I. It's probably useful for you to just know what these are. Of course, I cross J is what? Right, so it's minus 6K plus 1 times negative K. So that's equal to Q times minus 7K. And Q for a proton, of course, you should just know that number. It's on your equation sheet, but the charge of a proton is 1.6 times 10 to the minus 19. Just as chemists, it's good for y'all to know that number. So fundamental unit of charge for proton times negative 7K. And so I can find the force on this vector is minus 11.2 times 10 to the minus 19. Coulombs. Or excuse me, not coulombs, newtons. And that's in the K direction. this would be going into the page. So if I were to draw this, it's in the negative k direction.
So
Negative k. So it's going into the page, minus k. Alright, so basic cross product. And then I can also find some other information about this. So let me look on the next page just a second. Let me see what I got here. Yeah, no.
So to answer what is the force vector notation, we just have to do the first part?
Right, this is the force in vector notation right here. Alright, but then I can also find the magnitude and the direction of the force. Actually, no, I'm sorry. I already have the magnitude and direction, but let's say I also wanted to find the magnitude and direction of V and B. This just goes back to vector stuff that we did before. Alright, I have V and B in vector notation, so I'll just do V right now, just to remind you how we do these vectors. The vector for the velocity was 2I plus 1J. Okay, so I can find the magnitude of that by Pythagorean theorem. And then I can also find the angle. So this vector V will be in the first quadrant. Something like this. I can find this angle theta. It's going to be the inverse tan of dy over dx. You'll see on some of the old tests that there are some, these vector type problems that we've done before, and you should be fairly well versed in them, but just make sure that you're up to date on them. And so that would be, in this case, the inverse tan of 1/2. Which is equal to 27 degrees above the plus x. Huh? No.
Cosine, never 2.
Right. Alright. Make sure you're up on your vectors, how to find magnitudes and directions and all that business. There's some homework problems to help you practice, and then the old test problems are a good practice for you too. Alright. Let's do this next one. This was a quick test from an old exam. You can try it on your own. Likely your exam problem would be a little bit more complicated. It'd have some other additional problems attached to it. Well, let's try this just to practice your cross product. I'll give you a head start. Doing our QV cross B here. In this one we have not just I cross J and J cross I, but we have some others. I always like to draw my coordinate system over here. You have I, J, K, and then you can use your right-hand rule to figure out what is the result of those various cross products. Also notice here that you'll have three terms that are related to your to the result, not just two like we had before. On the foil, which of these goes away? Which one?
Oh.
The outer, right, the 2 times 8, yeah. So this 2 times 8 is equal to 0. So that's my outer. Just fill. I'm going to go.
If we change that F to PH,
You would have an ABS, but that wouldn't make any sense. Alright, so that's going to be 12 J cross I. Plus 18 K cross I. It's very important that you write your operands and the cross product in the correct order. And then 24 K cross J. What is J cross I equal to? Alright, that's negative K. K cross I? K cross I is what? It's just J. Let me show you. It's positive J.
If you do that matrix mathematics, this comes out a little easier. But if I have K out of the page, I is to the right, so J is up. And then this K cross J, what is that? K cross J? It's negative I, right? So K is out of the page. What is it? Negative I?
Don't twist your hand.
Yeah. I always do it this way. So yeah, it's negative I. It's like this. Negative I.
Alright, and so that's it. We just do this multiplication out, and I get 10 times 12 is 120. I'll lose the negative because it's a negative K. Minus 180J. Plus 240I. That's in newtons. Alright, and by the way, if you wanted to find the magnitude of this, I don't know that we've ever done this before. I think I might have mentioned it last semester. But if I have a 3D vector, how do I find the magnitude of a 3D vector? Well, it is in unit vector here, right? 240I minus 180J plus 120K. How would I find it? The magnitude? Pythagorean theorem. But what is, I mean, we've only used the Pythagorean theorem in 2 dimensions. How does it look in 3 dimensions? It's what? No, it's not computed. It's basically you just add another squared term. So if I wanted to know the magnitude of this force vector, it would just be the square root. I'll write it in IJK of 240 squared plus 180 squared plus 120 squared. Okay, so that's the magnitude. The angle is a little more complicated than that because you have to find actually, what, 2 angles? 3 angles.
Just leave cosine square, cosine alpha, beta, gamma, and then you basically use whatever your magnitude divided by that. First cosine.
Right. Right. We're not going to do that though. Okay. But you could be asked just to find the magnitude of it. Mostly you're just going to express it in vector notation. All right. Ever been on cross products? We'll see it on the exam. It'll come up. Likely to have some additional problems in it. Like, if you have a cross product problem, you also probably have to answer some other things. But we'll see some examples of that in the homework, all the exams and what have you. All right. Look at the magnetic force. What's up?
I was gonna tell you that it's 323.
Oh, okay. All right. Okay, so this is a force, previously the F equals QV cross B. This is the force on a particle that's out in free space, a charged particle out in free space that's going through a magnetic field. But you can imagine that if I have a particle, a charged particle, within a wire, confined to a wire, that it would feel a similar force if it were moving through a magnetic field. And so a charge moving through a wire, we call that a what? A charge moving through a wire? We call that current, right? So anytime we have a current in a magnetic field, it will also experience a magnetic force. And we can calculate that in this way. It's going to be I times L cross B, where L is the length and direction of the wire. We can think of it as the length and direction of the current if you wish, but really current is a scalar quantity, and it's really the length that's the vector quantity here. So L is the length and the direction of the wire in vector notation. And so just like we had before, oh, by the way, if you look at this, before we had, well, let me write the magnitude. This is ILV sine theta, just based on our definition of the cross product. And remember before we had F equals QVB sine theta. Well, you notice that these two parts are identical. Those two parts are identical. But we can compare these two and just do like say a unit analysis on these, and you'll find that they're the same too. So I is in coulombs per second, and L, which is a length, is in meters. Q is in coulombs, and what's V? All right, it's meters per second. So notice that these are also the same. So these are the same scenarios. We just constraining our charged particle to a wire now instead of having it out in free space. This is going to be the idea behind electric motors and electric generators because I have these forces and I have these currents flowing, and so in a variety of ways we'll be able to get these to produce either an electric motor or an electric generator. We'll return back to the force on a free particle because that's going to be important for a particular device that many of you will use, mass spectrometer. We'll see. All right. Okay, so what's that? All right, you're getting steps back. Thank you, Catherine.
So, what is Catherine?
Huh?
What is her role? She's not the electrician, she's something else.
She's the paper pusher or something.